Hello everyone. In the last lecture, we learned about how concurrent testing and execution generative testing did work. Also, we learned the two main challenges in symbolic execution. So in this lecture, we will continue to learn white box testing and in particular, introduce one key technique for attacking this main challenge in symbolic execution. So let's start with this week's lectures. Today, I will start with a brief review of an open challenge, namely path explosion problem we learned last time. Then in this lecture, I will introduce a key component of symbolic execution, namely search heuristic or search strategy. So actually, there are a lot of lines of researches for employing search heuristic in symbolic executions. So let's learn some well-known and effective search heuristics, including the state-of-the-art techniques, which is mine. Okay, before introducing what a search heuristic is, let's refresh why we need these techniques. So we usually need search heuristic because of the path explosion problem. As I mentioned in the class last week, the path explosion problem is that the number of execution paths is exponential in the number of branches in the programs. So let's look at these toy programs. So in this code, there are 4 branches, and suppose that we treat all the integer variables x, y, z as symbolic variable. So my question is, how many execution paths are there to explore? Yes, the answer is 2 to the 4, which is 16. Again, another question. Among the 16 paths, what is the number of execution paths for reaching the error locations? I give a 5 seconds to find these answers. Yes, the answer is only a single execution path that is able to exercise 4 true branch conditions in this code. That is, if we blindly explore the execution path even in this toy code, the probability of reaching the error is 1 in 16. Of course, exploring 16 paths is really trivial things. So let's change this toy code a little bit more difficult. So suppose that this modified code takes an integer array with a total size of 100 as input and has a total 101 branches. So also we treat this integer array as symbolic value. So in this modified toy code, what is the total number of execution paths? And how many execution paths are reachable for this error? So again, I give 10 seconds to find these answers. Yes, the answer is the number of execution paths is 2 to the 101, and still only a single execution path is able to reach the error. That is, the probability of reaching this error in this toy code program is almost 0 when blindly exploring execution paths. Moreover, when testing real-world program having more than 10,000 branches, it is almost impossible to find bugs without a proper handling for path explosion problems. So many different techniques have been proposed to mitigate these path explosion problems. So the first technique starts from simple questions. The question is that among the numerous execution paths, which execution path should we explore first for effectively increasing code coverage or finding subtle bugs in the programs. And the techniques, namely search heuristic, is the answers. And the second question is slightly similar to the first one, but opposite. The question is that which execution paths are redundant for finding bugs or increasing code coverages? And to answer this question, there are two main technologies, namely path pruning heuristic or state pruning heuristic, and path merging heuristic and state merging heuristic. So today we are going to focus on the first technique, search heuristics. So note that all practical symbolic execution tools such as CLI or CREST employs the search heuristics either explicitly or implicitly. So let's see what the search heuristic is in conflict testing context. The job of search heuristics: first, select the branches to negate that are likely to maximize code coverages or find bugs. So each search heuristic has its own criteria to pick a branch first. For example, when there are 3 branches in the current path, depth first search DFS heuristic will choose branch 3 based on their criteria. And if we're using BFS heuristic, BFS will choose B1 on its own criteria. In this lecture, we explore the well-known and effective search heuristics for conflict testing. The first 3 search heuristics have already been briefly introduced in the last paper presentations. And the last search heuristic is the state-of-the-art search heuristic for conflict testing. And actually, this is my technique, so I will explain it in a little bit more detail. So, okay, let's see how each search heuristic works and its intuitions. The first heuristic is control flow directed search. It usually calls CFDS. And the CFDS heuristic came from the natural intuition that uncovered branches near the current execution path will be easier to exercise than the uncovered branches far from the current path. For example, suppose that in this figure below, the red branches denote the covered branches already, and while the blue branches are the branches that have yet been covered. So given the current execution path, passing the 3 branches B1, B2, B3, so which branch B4 or B8 is easier to cover at this path? The answer is B4, because the branch B4 is closer to the current path than B8. Of course, uncovered branches close to the current path are not always easy to reach, but this CFDS heuristic usually expects them to be easy to reach. So CFDS heuristic aims to first select the branches to negate that are close to uncovered branches at the current path. To do so, it first calculates the minimum distance from each branch in the current path to uncovered branches. So there are 3 branches, B1, B2, and B3 to negate in the current path. So let's calculate the minimum distance of each branches. So when selecting B1 to negate, as you can see, we are not able to any uncovered branches in this case. So we calculate the minimum distance of B1 as infinite, unreachable. Second, when selecting B2 to negate, we are able to reach uncovered branch B8. And as there are 4 branches to reach from the branch 2 to branch 8, we calculate the minimum distance of B2 as 4 in this case. Lastly, when selecting B3 to negate, we are able to reach uncovered branch P4 directly. So we calculate the minimum distance of P3 as 1. So we select the P3 to negate since it is the closest to the uncovered branches. Then the current path is passing through the another 3 branches, B1 and B2 and B4. And now there is only a single uncovered branches, B8. So in this time, we select B2 to negate that the current path is as follows, B1, B5, B6, B7, and B9. And likewise, we calculate the minimum distance of each branches and then select B9 as it is the closest to the uncovered branch B8. In this way, the CFDS heuristic aims to reach the uncovered branches effectively. And in my personal experience, this heuristic has a good intuition and it is usually effective for testing real-world programs. Okay, the second heuristic is generational search. This heuristic came from the following questions. Which branch has the highest coverage gain in the current path when negating and executing the branches? To answer the question, this generational search follows the natural intuitions. More specifically, this heuristic repeats these 3 steps. First, it negates and then executes each branch in the path. And second, it calculates the coverage gain of each selected branches. Lastly, it selects the branch first with the highest coverage gains. For example, the branch coverage gain of branch 1 is just 2, and the coverage gain of the B2 is 4, and the last branch B3's coverage gain is just 1. So this technique will select B2 with the highest coverage gain in this case. Again, given the new current path, the generation search heuristic repeats these 3 steps again. So in this case, as the coverage gain of B5 is the greatest, so this heuristic will choose B5 in this time. In this way, the generation search aims to guide conflict testing toward the highest incremental coverage gains. And the next search heuristic is context-guided search heuristic, presented in FSE 2014. And the branch selection criteria of CGS heuristic is to first select the branches having new context. So in this work, the context denotes a sequence of preceding branches in the current path. For example, one depth context of branch P6 is P4, as P4 is the preceding branch of P6 in the current path, as you can see. And if we considering the second depth context of P6, it will be P4 and P1, as you can see. So using this context of each branch, CGS heuristic guides conflict testing to select the branches first, having the unseen context before. So let's say we have explored the current path as shown in the lower left. Then my question is that which path has new context of P6 among the path 1 and the path 2 in this case? In this case, compared to the current path, the path 2 has new context as the context of P6 in the path 2 is P3, which is different from the context of the current path. So CGS heuristic prioritize choosing the path 2. That is, CGS heuristic prioritize the paths that are most different from the explored paths so far.